To this session of Shadow the Scientist. My name is Jamika Marshall, and I'm very pleased to serve as the Shadow the Scientist Programs Manager. So we're looking at your face. It looks like something just happened. So let's jump in. We are going to be shadowing tonight the always stellar observing team at the Gemini North telescope. And our science host tonight is going to be Brian and Anik. Brian, go ahead and get us started. Aloha, welcome.
Aloha, Jamika. How's everything up there at the Viz?
It's cold and socked in, so you have a crowd of people here. Oh, you can see behind me, crowd
Everybody
here, and there's some on the other side, but I'm mirroring two screens here, so I don't want to unplug things. But yeah, we're excited to hang out with you all because it's cold and cloudy here.
Yeah, we have a view of the summit right now. It looks cold and cloudy up there. So hi everybody, I'm Brian. I'm a staff scientist at Gemini North Observatory. This is Anik behind me. We're the observers for this evening for Gemini North. We also have Jenny over here. She's the operator for this evening. So yeah, we're staff at Gemini North Observatory. So maybe some people have seen it, maybe not on tonight, but some people have seen it up at the summit. And we are getting ready for tonight's observations. Unfortunately, as you all know, the road is closed up there, I think, and the humidity is quite high. And so we are just doing preliminary checks of our telescope and instruments in preparation for hopefully observing later this evening. So Anik and I are the ones with the cosmic roadmap tonight, where we at Gemini we do what's called Q observing. So that means scientists from all over the world propose ideas for this to observe with this telescope. Some of those ideas are rated as being very good, and they get the opportunity to have a chance at observations with our telescope. And so we have a slew of programs tonight, scientific programs that are matched to different conditions. So there are some programs that can take very cloudy skies. So tonight it's pretty cloudy. So if we were to open, we would observe brighter objects. So those types of scientific programs would be maybe like local stars or really bright local galaxies in the local group or a little bit beyond, all the way to very beautiful skies, clear skies, non-turbulent atmosphere, where we're looking all the way out to the observable universe. And so we have about 13 different maps tonight, depending on the weather. And so if we're able to open, then we would follow that roadmap. Jenny is the one driving our telescope. And so she's in charge of safety, first and foremost, both of the night crew and of the telescope and the instruments. So she's going to keep an eye on the humidity right now. Actually, the humidity dropped quite a bit. This is pretty normal for Mauna Kea at sunset. But I can show. Actually, I guess you guys have cameras up there, but let me show our cameras.
Yeah, we have cameras up here, but yours are better. Ryan, Anik, Jenny, please show us yours.
Yeah, so I'll share some. Okay, so this is the Gemini North status page. Whoa, okay, that's new. So this is a public page, actually, so anybody can go to it. If you search on Google Gemini North status, this page is available to people. And this shows right now, currently, what things look like up on the summit. And there's tons of information here. This is really useful because I actually didn't introduce the fact that we're down here in Hilo. So we're at the base facility. We're near Emiloa, across the street from Emiloa, if people are familiar with Emiloa or with Hilo. We're right on the University of Hawaii Hilo campus. And of course, the telescope is up on the east ridge of Mauna Kea. And so we are not there at nighttime. Nobody's actually physically at the telescope for Gemini North. That's other telescopes, Keck and Subaru, have people up there most of the time, but we don't. And so we need a lot of electronic eyes, sensors on the summit and on our telescope to be able to make sure that we're doing things safely, and then also that we're assessing the conditions correctly so that we know which scientific program we would observe on at a given point. And so this has a ton of information. A lot of it's for us. So like, for example, the relative humidity here, temperature, wind speed, the directionality of the wind. This thing here that just popped up, this is a application that tells us how thick the clouds are that are going above the summit, or generally over Hawaii and the Big Island. And then these are all our cameras, our super light sensitive cameras. Well, that's really crazy. It didn't used to do that. It's kind of disorienting. So we have an east-facing camera, so facing towards Hilo up here at the top, south-facing camera towards the cinder cone, and then this is IRTF, so facing west. Oh gosh. Sorry. And then we have IRTF and Keck 2 here, and then our up-facing camera. And so you can see that the inversion layer is basically right at the summit. And so we're hoping that all this stuff gets pushed down below the summit later this evening. And then we're just left with these higher clouds up here. So you can see on this page that we are closed, and that's unfortunate because we always like to be open. But if we have the opportunity to open, then we have a bunch of exciting science planned for tonight. So this is the Weather Center page. I think this is available up in the Viz and probably right behind the cashier. They display it. But this is just showing sensors from all the different telescopes. And red is bad, of course. Bad for telescopes, bad for people going up to the summit. But good if you want to hang out at the Viz and watch us talk about astronomy. So maybe, Jamika, we could open it up for questions, and then
Panicked for a second. You said open it up. I was like, no.
Well, let's go. Why not? It's dropped to 97%.
Oh, humidity went down 2%? Is that what
It's like fluctuating all over the place right now. So it's yeah, we're not going to open at least within the next 40 minutes or so.
Okay. All right. Well, before we take questions from the amazing crowd that we have here, and also those of you who have joined us virtually, I just put in the chat that you can post your questions and comments in the chat anytime. They'll come directly to me. It's one of our security filters, but I will share it with everyone so that Brian, Anik, and Jenny can see it. Brian, since we got an introduction from you, could we get one from, if they're willing, Anik and Jenny?
Yeah, of course.
Okay. Yes, Anik, welcome.
Hi, everyone. My name is Anik. I'm a science fellow here at Gemini. So that means I mainly do research. But tonight I'm observing training with Brian. So that's very nice.
You're a prize fellow.
A prize fellow.
A Noir Lab prize fellow, don't understand.
Yeah, so it's pretty fun. So that basically means I get paid to just do whatever I want, as long as it's astronomy related. Yeah, so I use data from many different telescopes, and I study very distant quasars. So I don't know if you're familiar with quasars, but they're basically like very massive black holes in the centers of galaxies, and they accrete a whole lot of matter very, very quickly. So they're some of the brightest things in our universe, and that means that we can see them very, very far out. So that's why I study quasars in the early universe. So with our telescopes, is the further that we look into space, so like fainter stuff, the further we look back in time, because light takes time to travel towards us. So that way, with like big telescopes like Gemini, you can observe stuff that happened only less than 1 billion years after the Big Bang. So that's pretty cool.
So like roughly when the universe is like 10% of its current age. So
yeah.
adolescents.
Mm-hmm.
Yep.
Yep. So that's pretty cool. Yeah.
That's very cool. That's very cool. Thank you. Thank you, Anik. And so Brian and Anik are in the observer's chair, the astronomer's chair. There are two chairs this evening while Anik is learning the ropes from Brian. But we have another chair over here to the left. Who's that over there?
Well, in the distance, I am Jenny, and tonight my job is operator. So I will, as Brian said, protect the telescope from the observers.
Observers. There's two
Even
of
worse.
us. Gotta fend us off even harder.
And they will tell me where to go and where to point, and I will point it and set it up, and then they will take the data. And so that's what I'll be doing overnight. Another portion of my time is spent doing what they're doing right now, which is observing. And then sometimes during the day, I'm helping get instrument calibrations and helping the day crew and the instrument crews get their work done and talk with each other, communicate with each other, and make sure nobody's stepping on anybody's toes, and checking some data to make sure that the previous night that the data we got was good enough to send off to the PI. And then sometimes I get to do side projects as well. So we have a very diverse job as a SOS, which stands for Science Operations Specialist. I always forget what that stands for, but I remember tonight to your benefit.
Yeah, so Jenny brings up a good point, which is that, so there's three of us in the room right now. But there is, what would you say, like 80 staff here, something like that?
Yeah.
80 staff. So there's about 80 staff that work at Gemini North and Gemini International Observatory, which is, we have 6 partner countries. Our other telescope, because there's a twin telescope or near twin, is in Cerro Chile in the southern hemisphere. So we can see the whole entire sky. And there's about 80 staff working there. So 160 staff working at the International Observatory and 3 here tonight. So you can imagine that there's a lot of people doing a lot of things at a lot of different times. And so Jenny mentioned the day crew. There are people that go up to the summit effectively every single weekday. They check on our dome. They check on our instruments. They do engineering work up there. It's really tough work. I know y'all are not on the summit tonight, but maybe you're already feeling the oxygen deprivation at the Viz. For anybody who's been up there before, unless you're superhuman, you can very definitely feel it. So it's tough. It's manual labor. It's cold. Usually it's windy. We keep our dome at nighttime ambient temperature. So that's 32 degrees Fahrenheit, roughly 0 C. And so, this is intrepid work that they do every single day. They drive up around 8 o'clock. They do what y'all were planning on doing tonight, which is acclimate at the Viz or at Halipaku, just up the road. And then they drive up to the summit and do their work all day long, and then come back down 5 o'clock at night, just in time for us to open up. And so one of Jenny's jobs is to coordinate all that work during the day, because when we get here at night, we need to know that everything's set up and ready for us to go, so that as soon as the conditions are right for it, we can open up and we don't lose any scientific productivity. So everybody at the observatory is on the same team working together, and we have like constant communication channels between us to say, yes, you're good to go. Yes, you can use this instrument. No, you can't use this instrument. Keep an eye out for this thing, so on and so forth. And so it's really a team effort. And we honestly have one of the easier jobs here, although it's like, especially in winter, these are long nights. We're nice and comfortable here in Hilo, and we don't have to, drive up and, be there. I've observed from the summit before, it's a lot harder to think up there.
It ages you.
Yeah. Yeah.
Excellent. Thank you so much. Yeah, that's me. Thank you. So we appreciate the introduction to everyone. We are super excited to be here with you all, and thank you for providing the background to understanding why you're closed right now. So that gives us a little bit more face time with you all, and I'm actually really excited about that. So our first question is about asteroid 2024 YR4. Did Gemini North or South, play a role in tracking that asteroid and helping to define its orbit, which led to, of course, the reduction in its percentage possibility for it to slam into the Earth, which is now nil, which is great.
Yeah, so I think so. So I'm not observing every single night. So like as we mentioned, I mean, first of all, like these are 14-hour nights. Like, I mean, we usually come in early and then we stay late. So it would not be human to be able to do this every single night. And so we switch off observing shifts, and like as Anik mentioned, we do research during the day. I use other telescopes. Anik uses other telescopes. We use Gemini North. And so the observations that take place here come from scientists all over the world. And like I support certain programs. So I will help certain teams that are successful getting time on Gemini. I will help them set up their observations. But as a staff member, I don't have a view of every single observation that Gemini takes, probably like 20% of the observations. There is a very prolific team that used a lot of the Maunakea observatories for that particular asteroid. I know Subaru was used. I'm pretty sure Gemini was used. I think Keck was used as well. Yeah, initially the uncertainty in the position, you needed a quite large field of view for, at least for a large telescope. So this is still like a little, tiny pinprick in the sky, but you needed it was faint. And you needed a fairly large field of view to see it. And so we have one instrument called the Gemini Multi-Object Spectrograph, which is a multi-utility instrument. It can take spectra, so basically break up the light into its constituent colors, but it can also just take an image. And so we do that. We use that instrument to monitor a lot of asteroids. And I think that was one of the targets from from a perennial user on Gemini, which was Bryce, I think, Jamika.
Oh, was it Bryce?
I think Bryce got some data at some point. Yeah.
Oh, okay.
But yeah, so
that would totally make sense, because in our last session with Bryce a few weeks ago on Keck, he did image 2024 YR4 and was super.
Oh, there you go. Okay. Yeah.
Yes. So,
yeah.
That sounds
yeah,
like
and I think he tried to get more images recently, and this just tells you how hard it is to get telescope time for these big telescopes. I think he just proposed recently for more time on Gemini to observe that target, and actually he was denied time. That there were proposals that had more scientific merit than that, and it may be because it went from 4% likely or whatever it was, 3.6% likely to 0.001. So people thought, well, okay.
Old news.
Boring.
Yeah. Right. That's really
it's not till like 2032 or whatever, so it's fine. We got time.
That's right. Okay, so we have a question about getting time on the telescope. So can you tell us how universities, organizations, individual scientists, people, how do you receive telescope time for observing at Gemini?
Yeah, so Gemini is like honestly one of the most dynamic and most inclusive observatories in the world. We have so many different pathways to get time on the telescope, and we are one of only a few telescopes in the world that allow anybody in the world to apply. So we have 6 partner countries, as I said. US is the major partner country, and the US National Science Foundation, who's the major funder of the Gemini International Observatory, they have a policy called Open Skies, which basically means that anybody in the world can apply through the US channels, and as long as your idea is good, you get time on the telescope. So the main way to do this, we divide the observing year into 2 semesters, an A and B semester. One goes from February to August, the other one goes from September to January. And you propose for time on the telescope, you write an actual proposal. Gemini is nice because a lot of telescope proposals, like the James Webb Space Telescope, although they recently changed this, or the Hubble Space Telescope, or Keck, the number of pages that you have to write to kind of prove yourself is in the neighborhood of 4 to 10. Gemini has 1 page. So you write your idea and you put some pictures and you try to prove that your idea is scientifically meritorious. A panel of scientists from all over the world get together at some point, and there's usually about 5 times the amount of proposals that we can accept. So we can accept like 1 out of every 5 or 1 out of every 10, depending exactly how they're proposed, like through which channel they're proposed and for which time of the year, what specific conditions, so on and so forth. And so they have to take all these ideas. This panel has to take all these ideas and say, yes, that one's a pretty good idea, but maybe not. Maybe they can try again next year or next semester. Oh, that one definitely, that's really good. Oh, that one's crap. Let's get rid of that one. And sift through and try to understand what would be the best use of the observatory for the science. And so that's one way that people can apply. We also have a program called Fast Turnaround, which people can apply every single month.
That's my personal favorite.
Yeah, it's
like astronomy. Astronomy is horrible in the sense that usually it takes a year going from an initial idea to finally getting your data, just because you can only apply usually once or twice a year. Then you have to wait for the panel to approve it, and then you have to wait for your observations to be scheduled. So it's kind of a slow motion business. So the fast turnaround program that Brian just mentioned, that's like my favorite, because that means that you can get a small proposal approved within a month, and you can get your data usually the month after already. Yeah. So within 2 months, you have your data.
And even small is like, I mean, it could be up to 10 hours, right? So it could be like a whole entire night, effectively. And as Anique said, like, yeah, I've helped program teams where they propose, and within like 21 days they get their data. This is like near unheard of for major telescope, like big telescopes in the world. That is near unheard of. And one of the other really nice things about Gemini is we have this queue system. So things are inserted into the queue, into this big pool of observations immediately. So once we get them ready, so if your idea is accepted, once we get them ready, which I would work with Anique to get her observations ready technically, and then we would stick them in the queue and they could be taken that night. Whereas for like the Keck Observatory, which is, I'm wearing their shirt, so I love them, so I'm not going to say anything bad, but they work mostly on what's called a classical schedule. And so you propose for time. They say, yeah, that's a good idea. We'll schedule you. Here are your 2 nights. So you're going to observe on August 27th and August 28th. And you say, great, that's awesome. I'm ready to go. It's February, but I'll work really hard between February and August to like get things ready. So I'll, make sure my idea is like still good. I'll check my other data. I'll work really hard on all the technical aspects. I'll put together some other observations that help me inform me like what my targets are going to be. And you get all the way up to that night and it's cloudy. And you're like, all right, well, I got one more night and then it's cloudy. And so then you have to wait another year and you have to repropose and you have to say, by the way, guys, my idea is still good. Please give me some time. And sometimes they even say no. They say, no, we're not interested in that anymore. And so you don't get your observations. And with the queue system, if your idea is ranked very highly, you basically have a chance every single night. And so that's, I have been on many classical nights where I've been leading the observations where we've been very, very disappointed. There are many benefits to the classical system as well, but that's one of the major detriments.
Really suck.
Thank you. Thank you.
If you're trying to do some research,
Yeah, that's right.
you gotta wait.
You have to wait. That's right. We were just, and possibly not get time. That's right. We were just discussing how frustrating it would be if it wasn't this Q system that you all have and you were on a different telescope and this is your night and you have 2 hours right now and
Exactly.
it's nothing. Yeah, just how frustrating, challenging that would be. Okay, so we have a question.
Sorry, one sec.
Jamaica, can you hear me?
Yes, I can hear you.
Okay, I was just gonna say, I've seen observers at Subaru fly in from Japan for their one night. And they're weathered out, and so they're standing on chairs and doing dances to hope that the weather improves, get their data.
Yeah. Anything you could do at that point. Yeah, I mean,
Anything to get the clouds to clear, even as superstitions or whatever.
bring chocolate for your operators so they'll open earlier.
But then if anything, you have a nice holiday in Hawaii.
I don't know if they take advantage of it.
Yeah, but like, for example, my research group has observations on Subaru on this upcoming Saturday and Sunday. So I've been checking the weather not only for observing on Gemini this week, but also for the weekend. And very luckily, it looks like it potentially will, these clouds and the humidity will clear out for the weekend and we can get some awesome observations. But that's it. If it's cloudy, if it's like tonight, then we have to wait. And we may not get that time.
Ah, yes. Okay. So, that's very illuminating for the people here to hear, and they can understand and empathize with the frustration of those who get weathered out for sure. Thank you for that. So next question is, how far can the telescope see? And so of course, that's going to depend on the kinds of images that you're looking at, right? The objects that you're looking at and the how many light years they are away. So perhaps you could tell us what's the furthest object you've looked at with Gemini, or an estimation, you can estimate.
So actually, Anik has used Gemini North for her own research more than me, and I've used it a little bit, but I haven't looked as far back as Anik has. So I'll pass to Anik to answer this one because she has a really distant object that she's looked at.
Yeah, if you guys remember me talking about quasars before, so those were the very, very bright supermassive black holes at the centers of galaxies. So because they're so bright, we can look at them like very, very far away. So I think these are some of like the furthest objects that we've ever seen. And we astronomers, we don't really talk in distance of light years, but we talk in redshift. So redshift is basically the wavelength of light becoming redder because of the expansion of the universe. So you can imagine that maybe light was blue first, coming from a galaxy, but because the universe has expanded, that light wave has literally stretched out and become red on their way to Earth. So we basically talk in terms of redshift, and it's like some of the highest redshift quasars, so the most very distant quasars that we have ever observed is around redshift 7, which is like, I think 600 million years after the Big Bang, something like that.
Yep.
7, yeah. So these are some of the objects that we've been observing with Gemini. Also for my own work, I think the furthest I've done is redshift 6.6, so that's very similar. So around like 800 million years after the Big Bang. So that's basically when the Big Bang, or when the universe is only like 8 or 5% of its current age. Yeah. So we can look at very, very distant stuff.
But Anik cheats because she looks at bright stuff.
Yeah, I look at bright stuff. Brian looks at faint stuff. But that means that you can't go that far. You can't go that far back.
That's your lensing.
That's true. Yeah. That's true. Yeah, we have like one hack, and it's called lensing. So it's when there's another object in between you and the object that you're intending to observe. And that's basically warping the light and also causing a magnification of the light. So it's increasing the brightness of the source and also changing the shape of how we see it. And that could be due to like any gravitational source. So it could be due to like a black hole, another galaxy, or another star, like anything that causes gravity. So some of the most very distant stuff that we've seen, we could only see because it was gravitationally lensed. And this is like a lot of these discoveries have been done actually for the first time by Hubble. I think Brian is trying to show you an image from Webb. Huh?
Magnifying glass.
Yeah,
Exactly,
totally.
yeah.
Yeah, let me share this. Probably people are familiar. Right, so probably some people are familiar with this one. This is a redshift 0.5-ish cluster. So this is a cluster of galaxies. This is like, so the foreground stuff, the white sources here. These are bright galaxies in the foreground. So these are local-ish galaxies. They're about 4 gigalight years back, something like that, 4 or 5. So about a third of the way to the edge of the observable universe. So local. And so this is some of the most massive structures in the universe look like this. So that you have a bright central galaxy here. You have tens or hundreds or thousands of galaxies that are all compressed into the same space as the space in between the Andromeda galaxy and the Milky Way galaxy. So it's a really compact environment with tons of galaxies moving very, very fast relative to one another, interacting with one another. And there's a lot of matter there. And the more matter there is, the more this lensing effect works. And so this is from the James Webb Space Telescope. This was the first image released by President Biden a while back. And you can see these really crazy looking things in the background here. These are all distant galaxies. And there's some really, really far away galaxies. This is one of them.
It's probably red if it's distant.
Yeah, I think this one here is one of the really crazy faraway galaxies. But basically, as Anik said, so there's a magnification, and it's just like a magnifying glass. And so you really increase the amount of light, the surface brightness of the light, by up to 1,000 times, can be.
Yeah.
And so a galaxy that you would never be able to see otherwise, you have this big telescope, you're helped out by this big, massive cluster that magnifies this light. And so you can see really, really faint galaxies at the edge of the universe because of the confluence of these two things. And yeah, they work in tandem. Yeah. So thanks, universe.
Yes, thank you, universe. This is a beautiful image. Thank you for sharing that to really bring home that point. And so we have a question about, so that was a JWST image. And so a question about Gemini. Can Gemini see outside of the galaxy? And we have someone who kind of may not have heard Anik when you were talking about your work with quasar. So could you explain again, can Gemini observe not only within our galaxy, but other galaxies?
Yeah, actually, I think most of the work that's been done with Gemini is probably outside of our galaxy. So that's what we call extragalactic research. And that's where we're looking at other galaxies or other groups of galaxies, for example, or other crazy stuff that we're finding out in our universe. Yeah, so that's like a big part of the work that we do, is looking outside of our galaxy.
Yeah, we have, so let's see, we have 3 different instruments tonight. So we have the telescope, and then we have instruments attached to the telescope. One of the instruments is called MAROON-X. This is a high precision radial velocity spectrograph. So it's to measure the chemical composition, the kinematics, so the movement, and the atmospheres of stars nearby. So that one's mostly confined to the disk of the galaxy and generally like the local neighborhood. but it's used to find exoplanets as well. So just like very detailed properties of stars that are nearby. And then we have two other instruments which can be used for localish stuff, including asteroids in the solar system. But GMOS, which I talked about earlier, the Gemini Multi-Object Spectrograph, a lot of that, so then what we call non-sidereal work, so the tracking of asteroids or comets, that's done with GMOS with imaging. But a lot of the spectroscopy, so when we break up the light into its constituent colors, that's all outside the Milky Way. And then we have the Gemini Near InfraRed Spectrograph, and that is used primarily outside the galaxy. And so at Gemini, on any given night, we look all the way from the solar system to the edge of the universe. We're lucky. So I'm sharing one screen here, and I'm going to embarrass Anik. So this is a press release from a couple weeks back, yeah. And this is Gemini North teaming up with a telescope called LOFAR to find a distant quasar, and then to see something really cool about it. So what are we seeing here, Anik?
Yeah, so what you're seeing here is this very cool radio jet that we discovered. So here in the center, so this is an artist impression. This is not the real image. I'll show you the real image in a second. But this here in the center is this quasar that I was talking about. So the supermassive black hole that's really, really, really bright. And then here we see two huge radio jets coming out of this black hole.
Pretty big, I guess.
And we've seen these radio jets a lot in our local universe, but we never saw this big of a radio jet so early on in the universe, when the universe was less than 10% of its current age. And that's why this discovery was so cool. So here you can see the real image.
Ooh.
So this blobby thing right there is some of the most distant stuff that we see with Gemini. So this is less than 1 billion years after the Big Bang. And this is that quasar. So this is that supermassive black hole.
But to be clear, this is not from Gemini. The picture is from Gemini, or no? It's from DECAM, right?
No, this is from DECAM. Yeah, this picture is not from Gemini. We use Gemini to take a spectrum, so to break up the light into different parts and to be able to say something about the mass of the black hole and how fast it was accreting.
Use GNIRS, right?
Yeah, use GNIRS. Yeah, so infrared. But yeah, this is just an optical image taken with a little bit of a smaller telescope, a 4-meter telescope in Chile. And then here in the yellow, you can see this image that we've taken with the LOFAR telescope. So LOFAR stands for the low frequency array, and this is a radio telescope. So that works way different from Gemini. So you don't have like a dome with a telescope in it, but you have like antennas. So this telescope is located in the Netherlands. The Netherlands is known to be one of the lowest countries in the world. It's usually almost always cloudy. It's always raining. So, but you know, Dutch people, we love astronomy.
You basically feel at home here.
Yeah, basically like Hilo, you know. So we were like, okay, so what can we do if we have this rainy country? We just build a radio telescope, because radio waves are just like photons with very long, like light particles with very long wavelengths, and they can go through the clouds. So we can actually detect radio from the universe with our antennas, with our radio telescopes. So this is done at 150 megahertz, which is very, very low frequencies. And it's actually similar frequencies that are used for your radio in your car, right? It's very similar to that, but we have specific bands that are protected where we can only observe the universe and not just listen to the radio.
Yeah, like 100 megahertz is radio, right?
Exactly. Yeah. So here you can see an image that we took in the radio with just the Dutch LOFAR array. So this is kind of a low resolution. And maybe you can imagine when we saw this thing for the first time, we thought that these two sources were unrelated. We thought like, oh, this is probably related to the quasar, and this is probably not related to the quasar. This is just some other faint blobby like galaxy in the distance and not really related. But then when we use the international LOFAR array, so this is using antennas all over Europe.
Was that always planned? Did you have to apply to get higher resolution?
No, so actually a lot of the data that's been taken with LOFAR is already taken with the international array, but the issue is not taking the data. Just like with Gemini, the issue is reducing the data. So it's basically getting the
SUSD is
computational
listening,
power.
right?
So it's like we have a lot of data already in archive, but we just don't have the computational power to reduce it. So the data was already there, but we just needed the computational power to reduce it. Yeah.
Okay, so you saw this, you had this image and you're like, okay, let's reduce it. And then you got it back and you said, oh,
Yeah,
cool.
exactly. Yeah. Yeah. I
Whoa.
mean, I was just talking to a colleague who does this kind of high resolution stuff. And I told him, like, we have this crazy bright object associated to this very, very distant quasar. So I think that would be really cool to make a high resolution image of. And he was like, oh, we haven't really done these kinds of sources, but yeah, let's just try it out, you know? So we just tried it out. So this international LOFAR array, it goes all the way from like Ireland to Poland. So it's basically like creating a telescope the size of Europe. And that's the only way at these low frequencies where you can get like this high resolution. So we got this amazing image here where you could see here the core of the quasar shooting out this radio jet here to the north, and here probably bouncing off of like some very high density material, causing this brightening at the edge. And then here in the south, we weren't really expecting to see anything, but what you can see here is if you draw this line, it's actually creating here a southern lobe as well. And this thing is huge. It's like 200,000 light years across, making this like by far the largest radio jet we have ever seen in the early universe. Yeah, so this was a press release that came out about a month ago.
So can you put that in terms of like the Milky Way? So Milky Way is about 30,000 light years across, something like that, in radius, I guess.
Okay, yeah. So it must be about like 7 times the Milky
7
Way.
times the Milky Way.
Yeah, this thing is
insane.
huge.
Yeah.
Yeah, so we're trying to get some follow-up data now. Like a lot of these discoveries that we're making, it's never really using only one telescope. It's usually using multiple telescopes and also multiple instruments, because they all give us different clues about the things that we're seeing. They give us different wavelengths, they give us different resolutions. Yeah, so
It's amazing how many times we're like thoroughly convinced about something. We look at some instrument or some wavelength of light and we're like, oh yeah, that's definitely, or some resolution. And you're like, oh yeah, okay, yeah, that's it. Like that's the picture. And you look in radio or you look in infrared or you look in optical, if you already have one of those two, and you say, oh, crud, the entire picture has changed. And that's one of the things that's so exciting about science, is that it like constantly causes you to reflect and reconsider the things that you think are real.
Brilliant, brilliant. Thank you so much. And in fact, you, by talking about this object, you answered a question that I was going to get to next, which are, what are some of the crazy, you know, amazing things that you see out in the universe? So thank you for that. This is fantastic. And seeing the artist impression and seeing the actual images too is pretty incredible. So I have a question. I have a question. Yes, but we had a kind of a follow-up question on this about the collaboration. So LOFAR goes from Ireland to Poland. So is this interferometer?
Yeah, exactly. It's like an interferometer.
Yes, please explain what interferometer.
Oh, sorry. Yeah, no, I mean, interferometry is like magic. It honestly is. It's like you're trying to model the light that you're seeing. So you have these different antennae that are picking up light. And you can imagine if light is coming from a specific direction, it's hitting some of the antennae before it's hitting the other ones. And just by like seeing the different responses in the different antennae from different sky locations, we're trying to model what the source was supposed to look like to give us that response. So radio it's very, very different from Gemini, where you're basically just collecting photons, right? So you're getting this direct image. Of course, you still have to deal with a lot of like instrument noise or like other things like the atmosphere. you still have to deal with a lot of that to like get clean, nice data. But with radio, it's just completely different, where you have these different antennae and you make them work together as a big telescope, and it's what we call interferometry.
Yeah, and Anik brings up a good point, like talking about the data reduction or like the processing of the data. This is what a lot of our time is spent on doing this, because you get an image at the telescope, whether it's a radio image or an optical image or an infrared image, and it has all these confounding factors. So it has, in the case of interferometry, you have to combine the signal. There's all sorts of false signal in the data. And so you have to clean that. You have to say, yes, that's astronomical source. No, that's some guy turning on their car. No, that's, there's all sorts of contaminants. And same thing for optical or near infrared astronomy. So when we observe from the ground. We have to observe through the atmosphere. If we're going outside the Milky Way, we have to observe through the Milky Way. We have optics on our telescope. We have our instruments, which have imperfect response. We have cameras, which have detectors, which have noise. And so we have to, a lot of our time is spent removing all of those issues to get to the truth of the source. And so we want to take away anything that's terrestrial, anything that has to do with our vantage point in the Milky Way, and get to the intrinsic properties of a source. And so that, as you can imagine, is very difficult, but we take all sorts of calibrations on a given night, whether it be sources up in the sky of known brightness, or measuring the internal properties of the detector, or measuring the properties of our optics, or even the attenuation of the atmosphere. So the atmosphere changes over time, and so it can increase in brightness, especially if we're looking in the near infrared. It can increase in brightness a lot. It can decrease in brightness. Different species, molecular species in the atmosphere can get excited at different times, especially like at right around sunset or sunrise. It can dramatically change. It depends on where you're pointing with the telescope. So you're either looking through more atmosphere if you're kind of pointed towards the horizon, or you're looking through less atmosphere if you're pointed straight up. And so that can change your view of the source. So you want to remove all of those technical aspects as best as you can to then get to the intrinsic properties of the source, because you don't want to be measuring something that's not real and then basing your science off of that.
Thank you. Thank you. All right, we have another question, and he's going to ask it himself. Come on over.
My question is about red shifting within the visible spectrum. Whenever you go from a source that has blue light and it shifts to yellow versus something that started as yellow, how can you tell that has been red shifted versus that's just the original source color?
Yeah, that's a great question. So one of the easiest ways is spectroscopy. So spectroscopy is you're taking like an optical spectrograph, which we have one here, but we have two tonight. But the main one that we use is the Gemini Multi-Object Spectrograph. And so this breaks up the light, the white light, into its constituent colors. It does so in a kind of coarse way. You can choose based on what your science is. You can choose how coarse you want to break that up. So you could do like, yellow, green, red, blue, or you could do like red and like a slightly different shade of red, slightly different shade of red. So like really, really fine gradations. And so generally people use the kind of coarser setting because especially if you're looking at distant galaxies, what you think are distant galaxies, they can be nearby stars as well. You don't want to break up the light too much because there's not that much light to begin with. So you really need every photon that you can get. But what you'll see a lot of times in these distant sources is a kind of white light level from the source, and then these emission lines. And these emission lines come from generally from star forming regions, or from black holes, or from shocks in the galaxy, or from thermally pulsing stars in the galaxy. And so there's a pattern that you can recognize. You can say, I think that emission line that I see there, or that combination of emission lines, I'm pretty sure that comes from hydrogen, or I'm pretty sure that comes from oxygen. And how would you possibly know that? Well, the physics, first of all. So you can calculate which species, given a kind of elemental abundance in a galaxy, which species should be excited. So which ones should be emitting and which ones shouldn't. You can go into the lab, or you can ask your lab friends to go into their lab and take measurements of the wavelengths that each element emits at, or molecule emits at. And so they'll tell you hydrogen is emitting at this wavelength and this wavelength and this wavelength. And so then when you measure your spectrum, you don't see them at those wavelengths unless they're not redshifted. You see them at a redshifted wavelength. But the ratio of the lines, so the wavelengths of the lines, will stay the same. And so if you see two lines and you say, I think that's hydrogen, and you go back to your lab friend, you say, okay, what were those lines again? Okay, those two. Okay, so I take the division of those two, I measure my lines in the spectrum, I take the quotient of those two, and I say, oh, those are exactly the same. There is the signature of hydrogen. And then I can know how much it's redshifted based on the difference between the lab wavelength, the thing we measured here on Earth, and what's measured for that galaxy. And then that gives me effectively a distance, because the further things are out, because the universe is expanding, the further things are away from our vantage point, the faster they move away from us, generally. Andromeda is coming towards us. Sorry, guys.
Brilliant. That was brilliant. We got a wow for that response. Follow up? No? Excellent. Excellent. Thank you. All right. So we've had a request to check in with Jenny on the weather. How's it looking up there?
Okay, so let's see. In the past 50 minutes, the humidity has been slowly declining. And when it gets below 75% for 40 minutes, I can safely open. If it's the kind of decline where we still have spikes of humidity where it shoots up very quickly and then back down very quickly, I have to be a little more conservative with that time. If the decline is very gentle and you can predict that it's going to continue being that way, then I can play with that number a little bit and open up a little earlier. So we just dropped it for below 75, 10 minutes ago. So we'd still have to wait probably at least another 20 to 30 minutes before with these good conditions, and then also with no summit level clouds, which in the west camera, there are a few that are hitting our pu'us and dispersing kind of close to us. And in the Hilo cam, there's a wall headed in our direction. And when that wall hits the ridge, it tends to come up and create very sudden fog. So I'm not confident that the humidity will continue to drop as it is now. Sorry. Sorry, everybody.
Thank you. We got some thank you so much. Thank you so much from our guests here for that response. Before you showed us the weather, we kind of got a view of the telescope status display. Could we go back to that and maybe talk about what we would be seeing there, and maybe highlight some of the things that some of the information that's there?
Yeah, sure. So just before we go to that, so as I mentioned, I think near the beginning of the session, we need to have a lot of monitoring equipment up at the summit so that we are confident that we can keep things safe, and also that we can assess conditions so that we can get the most scientific leverage out of a given night. And so Jenny was monitoring this tool right here, which is what we call strip tools. There's all sorts of information on here. These are not active right now. These four because we are not on sky, meaning we're not open. And so these are all to measure things of the astronomical source that we're interested in. So those will remain dormant until we open up later tonight. When we open up later tonight. But this is the strip tool for humidity. And so the line here, this dashed yellow line right here, this is the 75% that Jenny was talking about. And this is the rise that Jenny was saying was likely to happen again.
Happen and poof,
Yeah, so she manifested.
we become meteorologists.
Yeah. Or extremely superstitious, one of the two.
Yeah.
And so we'll keep an eye on this. It's really bouncing around right around the level that we would be comfortable with. And so the hope is that things continue to clear up and we can open maybe within the next hour or so. So that's how we keep an eye on things, or part of the way that we keep an eye on things.
We also have a Slack page, a Slack team that most everybody on the summit who works overnight uses it. But it's just kind of a way to chat and communicate with each other in real time, so that we're stuck down here in Hilo and we're relying on our cameras and our sensors and other people's sensors. But occasionally we need somebody who's actually up at the summit to actually walk outside with like IR goggles or a flashlight and tell us what's really happening, so we can confirm what we think is happening. And in the past, in the past, I'd say half hour, Keck has mentioned that they see gaps in the clouds, so they're pondering things. They're a little more like cowboys in the sense that their telescope dome can open and close really fast. So if a fog bank comes in, they can just shut instantly. Whereas it takes us a little longer to shut things down. And so we have to be a little more conservative with that. And then CFHT, they're on the ridge as well. So we're always curious what they're up to. And they said that it's looking bad out there and they probably won't open till the clouds recede. I believe they're also on the summit. Is that right? Or are they remote now?
CFHT, sometimes they go up, but I think most of them are remote.
Okay,
Yeah.
yeah. So we rely on people who are there in person, and we all kind of talk to each other to make good decisions based on what we think is about to happen or will happen.
Just type in like archive.
Thank you so much for those extra details, Jenny. Wonderful, wonderful. We had some sad faces here about the outlook, but we appreciate the info. And
Right, we do sessions every month, and public sessions every month, and y'all are welcome to join us anywhere in the world. Show the images that we take on any given night.
yeah, that's right. That's right. So you all have my cards. Everything will be on our webpage when we have our next session with Gemini. But we are really grateful to have collaborations with many of the.
If anybody in the back building, please call 2634. 2634.
Yeah, so if you just grab my card if you have one. So on the back is the QR code, and then you just check our website. I'll be posting April sessions towards the last week of March.
Don't forget to plug Astronomy on Tap.
Oh yeah.
Oh, yes. And if you're, thank you, that's right. And so if you're in Hilo, if you're in Hawaii, April 3rd, we are going to be doing Astronomy on Tap. This is hosted at the Tavern bar down in Hilo, and we'll be doing a live Shadow of the Scientist session there from 7 to 9. So if you're in town, come and join us. But pardon? I am not going to live stream. I mean, it's going to be on Zoom, but it'll be a closed session. So you won't be able to join virtually. You'll have to come in person, and it'll actually be the 1-year anniversary of Astronomy on Tap, which was started by in Hilo, about a year ago. With Gemini. And lots of
It's a family-friendly event, so don't worry about bringing your family. You can stay all the way to the event.
To the end. Yeah, that's right. Thank you for that reminder, Jenny. Thank you. But yeah, Brian and I are the host. So we're excited about that, aren't we, Brian? And looking forward to it.
We're stoked. Yeah, ready to
See
go.
multiple control rooms that night, right?
Yeah, that's the big reveal. The four
I
control.
have not said that. Was that a secret?
No secrets.
Four control rooms that night. CFHT, Keck, and LCO, and Gemini.
Yep,
It'd be
Yep.
fun.
it's gonna be awesome. It's gonna be awesome.
Are you guys looking at any of the webcams right now or no?
No,
Yeah.
we're not. Please show us. We have more people who have come. Oh my gosh, it looks like things are changing.
Yeah, fog bank just hit. We just skyrocketed to 100%. That wall that I told you about that I was so scared of, it comes so fast and then bam. And if
There's
we were
the-
open, we would have been screwed. So
Yeah, there's the fog bank that just came in. So we're right on the edge here, and tip not in our favor right now.
But we can still show you a cool image that we took 2 nights ago.
Yeah, so I'll just quickly orient people on what I'm showing here, and then we'll go over to one of our other screens, which shows an image that Anik and I took. Anik, Jenny, and I took 2 nights ago.
Awesome.
So we have two chairs here, or sets of chairs. The observer over on this side of the room, and the operator on that side of the room. Each one of us has 8 screens. And so there's just all sorts of stuff, all sorts of information that we keep track of. A lot of Jenny's screens.
8 screens has an additional 5 screens within those screens.
Yeah, there is so much information. And so this is why we have to divvy up, in part, why we have to divvy up the roles, because there's just a lot of stuff to keep track of. And so then this is just one of the 16 or 21 or hundreds of screens that are available to us. But this is a really important one. This is the telescope status display. And this gives us all the information on what's happening with the telescope right now. So there's tons of numbers on here. Some of the numbers that are important are the current RA and DEC. These are the 2 coordinates up in the sky. So this is like longitude and latitude on the sky. And then there is information about the seeing. So basically, if you have a infinitesimally small source on the sky, like a star, and a star is very, very big, but it's also very far away. And so it basically looks like a point up in the sky. So this is why, like in the James Webb picture that I showed earlier, there's these diffraction spikes because these things are so small that they basically confuse the optics. And so if the atmosphere and the ground, if there's very little turbulence, the seeing will be very good. So a point source will look very small. If there's a lot of turbulence in the atmosphere or on the ground or both, it'll blur it out. And so this is something that we keep an eye on all the time. This is in units of arc seconds. So this is 1/3600th of a degree on the sky. Degree is about the size of 2 full moons. So this is very, very tiny. 1/1800th of a full moon. And so normally we like to see values that are around somewhere between 0.4 and 0.6. That's reasonably normal, on the good end of normal at Mauna Kea. And Mauna Kea is one of the best observing sites in the world, so that's kind of normal for us, but that's exceptional for pretty much anywhere else in the world. Down here is a rendition of our telescope. So this is actually where our telescope is pointing. So we're basically looking on top of the dome, or that's the rendering. Telescope is pointed straight up right now. And so that's what this dashed circle is. And then the dome shutter, if it were open, it would be this black thing right here that would extend all the way to where our telescope is. And so we have various wraps that connect our telescope to various electronics. We have, so this is a side view of our telescope with the primary mirror down here, the secondary mirror up here, a tertiary mirror down here in what's called our Cassegrain cage, or our instrument cage. And then we have all of our instruments, all the instruments that I talked about earlier, the Gemini Near InfraRed Spectrograph, Gemini Multi-Object Spectrograph, MAROON-X, the visitor instrument. Our adaptive optics mirror is also in here. There's an acquisition camera. So this is where we take, so the light comes in here from the distant object. bounces off the primary mirror, goes to the secondary, goes into this Cassegrain cage, and then is redirected to one of the instruments. And so, as Anik said, yeah, we took awesome image the other night. So that's this one here. So this is a relatively nearby galaxy. This is NGC 4958. So it's, yeah, let's say probably around 300 million light years away. So again, very, very close on by universe standards. So it took light 300 million years to arrive at the telescope. So this is what a picture of this galaxy 300 million years ago. So not now, but 300 million, but we took it now, or 2 nights ago. And so this is what that galaxy looked like 300 million years ago. So yeah, and so this is with our Gemini Multi-Object Spectrograph, but in imaging mode. This was a R-band image, so a kind of how humans would see it would be kind of red. So we put filters in front of the imager, and those filters only allow certain wavelengths of light, so we can take different colors, basically. And so this is more or less what the human eye would see as red. The color scheme that you see here is not the actual color scheme of the galaxy. This is just something we use to be able to pick out things at nighttime. And so
you can see how different this looks from an actual image that we will publish in a paper, right? Or like a thing that you would see on internet, on newspaper. Like we still need to do all the reduction to get this to like a nice image.
Exactly.
But I think the cool thing is that you can already see all these streaks of like dust and bands in this galaxy, right? Like even without reducing the data, you can already see so much structure.
Yeah, so as Anik said, there, I mean, you can see so each one of the, so we have 3 different detectors on GMOS. So basically, it's kind of 3 different cameras together. And you can see there's actually like, it breaks up along these like horizontal bands. These are different amplifiers for each one of the detectors, and they read in the light in a different way. And so there's actually offsets between the illumination, more or less. Or the response of the detector for a given illumination. And so this is one of the like million things that we have to correct when we want to get like a scientific ready image, not just for press releases, but for like actually doing the science. All of this needs to be corrected because this is all terrestrial. This is all just due to the imperfections. This is super sophisticated equipment, but it still has imperfections, and so we have to remove those imperfections in order to get to the intrinsic nature of the source, or the person who proposed for these observations and who got these observations will have to do that.
I get asked a lot, what's the coolest thing you guys have seen when you were observing? And I'm like, you mean the blob on the screen? Yeah, cool. But
Me and Anik are looking at. Yeah,
what's that?
that's what me and Anik are asking to look for.
Yeah. And then, but then if you are used to looking at those images before they're reduced, you can already tell, like they said, you can already identify some characteristics that it has that you know are going to pop out once everything's reduced and all of those imperfections are removed.
I always get excited about asteroids because you can blink between 2 images and you can actually see it moving.
Totally.
So whenever we're imaging asteroids, I'm like, oh, cool, you can see something moving.
Yeah, it's pretty rare in astronomy that you get to see things like actually moving, even though they're moving like thousands of kilometers per second. We don't see anything over human timescales.
Right,
They're
right.
distant.
So we have 2 follow-up questions about this image. One is, can you, sorry, Loke, sorry, can you come ask your question?
Okay, where do I go?
Yeah, just come right on over here, because you were talking about, can they age it, but I want to convey it properly. Yes.
So this is an image of a galaxy 300 million years ago or whatever.
Yeah. 300,
Yeah.
like,
300 million light years away. It's not what it looks like now.
right.
Can you age the image and to make it what it would look like now.
Hmm, is that possible?
That would be cool.
That would be-
but then we would need a time machine 300 million years into the future.
Yeah.
You could use modeling.
Yeah, so
have
the- like-
people who specialize in that.
Exactly. Yeah. So a lot of times, like, I mean, there's people in the astrophysical community that do simulations, or astrophysical models, and then there's people that take observations, and there's people that do both. And so one of the things, so this program, I think, so right after we took this image, this was actually just to set up on the observation. So we took this image and then we went to long slit. So we dispersed the light after this. And one of the things you can get from dispersing the light is the kinematics of a galaxy. So you can actually measure the rotation, for example, of the stars and the gas in the galaxy. And those, so you can say, that set of stars or that gas clump or that dust clump is moving at 1,000 kilometers per second, or for a galaxy, it's usually about 200 to 300 kilometers per second. And this can be input into models that then can show the future, potential future, given the constraints. Thanks. Of this galaxy. But then stars live and die on those timescales. So 300 million years, the brighter stars, so like the really, really massive stars, the really blue stars, those will die on timescales of like 10 million years. The little bit less massive stars will die on roughly 100 million year timescales. Stars like our sun will live to 10 billion years, so they'll still remain. But you actually don't know when those stars are formed, and so there's a lot of uncertainty associated with that. So instead of modeling one single galaxy, although that does happen, usually what people do is build up a sample of galaxies. So they look at a lot of different galaxies at a lot of different times in the universe, and then they try to make, it's all pictures of the galaxy, of different galaxies, and you try to take all these snapshots and say, okay, maybe this one would turn into this one, or this set of galaxies are the possible descendants of that galaxy. And so you can make like statistical models that tell you like how a galaxy would evolve, or how it formed.
Can I mention something really quick?
Yes, please. That was brilliant. Thank you.
This is unrelated, but I just looked in our west camera, and even though the summit is covered in fog right now, JCMT is open.
Yeah, that's good.
And so their dome is open, but they have a, I think it's made out of Kevlar or something like that, a screen that protects their telescope from like unwanted droplets or debris or anything like that. But because of the wavelength that they're observing at, they can see through that screen and through the fog, and they can still observe right now.
Yep.
Which is, I'm jealous.
So yay, radio telescope.
Yeah, it's more like a
I think it's
radio
crazy.
telescope in that sense.
Yeah.
Okay, so that makes us feel good for JCMT, and we're still like that is not quite for us. Yeah, but that's okay. That's hopeful. That's hopeful news. Back to that image, we had one more question about the characteristics that. Do you want to ask your question?
It was really just the characteristics they look for.
So what characteristics might might be looked for by the science team here? I know this is embargoed information, so you can't really talk about the specifics, but what might they look for that could be interesting here?
Let me double check what this program was actually looking for. Give me 1 second.
Also mention what, not as a scientist, but as an observer, what you would look for to pass that as a
Yeah.
successful.
What oh, this was this a 24B program? Yeah, it was. Oh, so we just completed this program.
Yeah. 409?
Yeah, so it's 24B 409.
And you can look up on the OT, the proposal for it, right?
Yeah.
So we're just
Okay.
looking up the proposal to see what the researchers wanted to do with this.
Yeah, so So as I mentioned, this isn't science that I propose for, but this is actually one of the other ways that people can get time on the telescope. It's a poor weather program. So 2 nights ago, we observed this and we were open, but there were still quite a few clouds. And so this program could accept those clouds because we're looking at a fairly bright galaxy. And so basically people write to our head of science operations and they say, hey, I have this idea to look at something while it's reasonably cloudy. And our head of science operations say, yeah, that's a good idea. We can do that. So that's what happened in this particular case. And so we took this image, and again, this image is pretty much just to get set up on the source. So on the galaxy in this case. And then we put a slit over it. So we just blocked out the slit probably went something like this. So across the galaxy in this direction. And so it got the central region of the galaxy and some of the spiral arms. And the reason you would do this is because you're just blocking out the light that you don't care as much about and focusing in on the light that you really do care about. So you can't get everything. There are observations called integral field unit spectrographs, which you can get spectrum of every single part of the image. But usually those are really they're relatively small field of view. So if you want a larger field of view, you would take, it's called a long slit spectrograph. And so they probably put it across the galaxy like this. And what they were looking for was something like hydrogen emission features in this galaxy were known to be fairly broad. And they were also known to be double peaked. And so what that means is there's multiple different velocity components in the galaxy, and there is a lot of probably outflowing gas, maybe from an active galactic nucleus, so like the kind of stuff that Anik studies, so maybe from an active black hole, or from stellar winds, so supernovae, from massive stars that have just died. And so they wanted to understand basically the kinematics of the galaxy and what was causing this blowout of gas is my guess. So I'm just looking at the title, and that's what I would guess based off of the title of the proposal. And then Jenny mentioned, so also it's not that when you take an image like this that it automatically is good. Like we have to assess it at nighttime. So we would look at a variety of different factors. So the first of which being, are we at the source that the person wanted? So if they proposed for a nearby galaxy and we see this, we say, okay, that's probably in the right place. We can check finder charts, and there's a lot of information that we have to be able to make sure that we're navigating to the correct place. But if we just see a little blob, then we're probably not in the right place. And so then we have to say, Jenny, did you a blob, or did you go to this really cool looking galaxy? Oh shit. Okay. Let me go to the galaxy. But then you also want to make sure it's not saturated. So meaning that you have so much light that the detector can't handle it and it kind of gives up, and there's this overflow of electrons that basically you lose information on the image. And so you can change exposure time, of course, just like you can with a normal camera. And so we would, if it was saturated, we would drop down the exposure time to make sure that we were, that we could see the galaxy pretty well. And then we do fine precision movements. So we'll take an initial image, and then we'll say we need to get right in that center there. So we'll move the telescope, nudge the telescope a little bit. There's cosmic rays, so high energy particles that hit our detector. If those end up in an unfortuitous location, we may have to retake the image. If a cloud, so that given night, the clouds were passing in and out. If a thick cloud goes over the telescope, we wouldn't see it, and so we have to retake the image. So all this kind of stuff we have to look at and make sure that things went well, and if not, then to re-slew the telescope, remove the telescope, or retake the image, or both. And so that's the assessment that we're constantly doing at nighttime.